All right, so I have started the streaming, and you can access the links via chat, or I have also pasted it in the calendar. Okay, so you can access it from the calendar also. So let's begin. Many things to discuss, and we'll begin with quiz 2 blueprint. So it's like what you can expect from quiz 2. It's a pattern, some sort of pattern. Okay, so I'll just quickly go through it. So the syllabus is weeks 5 to 8. Having said this, even week 4 will also be an internal part of week 5, right? So that is also there. Okay, so majorly the syllabus you can treat it as weeks 5 to 8, and the total marks is for 40. Total time given to is 60 minutes. And if you see weightages, you will have slightly bigger weightage for week 7 and week 6. And week 6 also, so week 6 and 7 carries more weightage. And week 8 carries, week 5 and week 8 carries a little less weightage. Okay. And in order to be, if I have to talk about questions, then it is same as quiz 1. So you'll have some straight questions without any comprehensions, and you will see them each carries 4 marks and 5 fours 20, and there will be 4 comprehension type questions, each carries 5 marks. So 4 times 5 is 20. So 20 plus 20 will sum up to 40 marks.
Excuse me, sir.
Yes.
So I think the quiz. What was the total score of quiz one?
This one is for 40, no?
Oh, that is also 40 marks.
Yeah, yeah.
Oh, actually, I assumed for the 100 marks. Oh, okay, sir.
It will be normalized to 100. But the paper that you are going to write, each question, the marks you see, if you total the marks, you will see that it will be 40. And it is multiplied by 2.5. Okay. So in quiz 2 also the same way. Alright, so let's come to the main agenda for today's session, which is the concepts that need to be revised with respect to week 5 and week 6 for quiz 2. Okay. So you definitely have to understand what derivatives and differentiability is, and you should know the differentiation rules and the linear and quadratic approximations. So from week 5, these 3 topics are really important. Okay, so that will cover week 5. And week 6 is applications of derivatives. So you should know how to compute local maxima, local minima, given any function to you. You should really understand Rolle's theorem and mean value theorem, and a beautiful rule which is L'Hopital rule, and also the Taylor's theorem. Taylor's, if you are unable to understand generalized Taylor's theorem, that is fine. At least the first order and the second order is important. Okay, so not beyond that. So you should know the Taylor series expansions or approximations. First order Taylor series approximation and second order Taylor series approximation is sufficient. Okay, and this will cover week 6. So these are also the important topics uh, that you have to revise for week 5 and 6. Okay, so let's begin. Let's talk about the theory. We'll just quickly go through theory and solve more problems. Okay, so why we are discussing theory again? So in order to bring everybody on the same page. Okay, so those who forgot what has happened in week 5 and 6. Okay, so you can quickly refresh here. So what is derivative of a function? And what is it? It is actually a limit value, right? So f is said to have a derivative L, capital L, at a point x is equals to x naught if this particular limit value exists and it is equals to capital L, right? So what is that limit value? It is limit h tends to 0. We compute f of x naught plus h minus f of x naught divided by h. Basically, the ratio of raise by run, right? Dx by dy. That is what we are doing. How much change happening in the function value when we change h units on the x value. right? So if this exists and it is equals to L, then we denote this as f prime of x naught, right? Only if it exists. If it exists, then I can denote this limit as f prime of x naught. And if f prime of x naught exists, what we can say? We can say that the function is differentiable at point x is equals to x naught. And if f prime of x naught exists for all x naught in your domain, then f is said to be a differentiable function. Right? So that is the definition of a differentiable function mean. Right? So when do I call a function differentiable? Only when the derivative exists at every point. Right? So we can quickly do the problem. So let's say if a function is given to you f of x is equals to x cube, and you are asked to find the derivative at x is equals to 1. So it is very easy, I know. If you know the derivative of x power a, it is simply 3x square f prime of x is, and you just have to substitute f prime of 1 x in place of here. You will see that 3 times 1 square is 3. But if you are asked to use the limit definition, then how do you approach? You have to compute the limit h tends to 0 f of, here x naught is 1, right? So this is x naught. So 1 plus h minus f of 1 divided by h. So this is the limit value. Limit I have to find, right? So I have to find. So this will be limit h tends to 0. F of 1 plus h is 1 plus h whole cube minus f of 1 is 1 cube divided by h. Now if you expand this, 1 plus 3h, 3h plus 3h square plus h cube minus 1 divided by h. So I hope most of you know what is a plus b whole cube expansion is. Right, so if you use that expansion, you will get this, and this will get cancelled out. H will get cancelled out. You will have limit h tends to 0. You will have 3 plus 3h plus h square. Now you can compute this limit, and you can directly substitute h is equals to 0, and you will see that you will get 3. And this 3 and this 3 is same. So even using the limit definition, you can get the derivative values. Or if you know the formulas, use the formula, get the derivative value. Okay, so sometimes this may not be this straightforward, right? So sometimes it can be complicated where you don't know the direct formula. Okay, maybe then you can use this limit definition. All right, so I hope this is okay. Then we also studied that derivatives can actually be defined as functions itself. Like, right? So given a function to us, and if we know that it is differentiable, then the derivative of that function will also be a function, and we denote it as f prime, right? So if you have a function f going from R to R, and you also know that f prime of x exists for all x, then this f prime is again a new function which goes from R to R. Okay, so for example, you can see here f of x is given to us as x power 5 minus 3x cube, right? So when I take the derivative, right, it is a polynomial function. We all know that it is very smooth. So derivative will exist at every point. So for this function, f prime of x will simply be 5x power 4 minus 3 into 3x square. Right, using the differentiation rules and all, we know how to compute the derivative. And this is a new function. You see, this is a polynomial of degree 4 now. Right? So 5x power 4 minus 9x square. Right? I can actually take one more derivative of this function. Now this is a new function and I can take, again, this is a polynomial. I can actually, again, the derivative exists at every point. And I can actually take one more derivative. Right? If I take derivative, what will I get? F prime of x is the function and derivative is like 5x power 4 minus 9x square is the derivative. Right? On the left side, this is f double dash of x. It becomes f double dash of x. It is called the second derivative of the function f of x. And this will be 20x cube minus 18x. Right? And can I take one more derivative? And this can happen. This can go. You can take one more derivative. Now the next derivative will just be a quadratic expression. And you can take one more derivative. It will just become linear. And finally, when you take a linear derivative, it will just become a constant. And when you take a constant derivative, it will just become 0. Okay, so this we have also seen during our regularizations, right? So these are called the higher derivatives of the function. So this is the second derivative, and then we will have the third derivative coming. When I take one more derivative, it will just become 60 x square minus 18. Right? I can take one more derivative and one more derivative like this. This can go. Okay, so that is looking derivatives as a function. So each time you take a derivative, it will just give us a new function, right? Another example is just e power x. I just took this example because we already learned exponentials, right? So if I take the derivative of e power x, I'll have g prime of x, which is e power x itself, right? So when I take the derivative of e power x will be my derivative also, right? So here what happened? Even my derivative function is also same as the original function. This is first derivative. And if I take one more derivative, on the left hand side, it will become the second derivative function. Even the second derivative function is also e power x. So like this, you can take derivative any number of times, but we'll get the same expression e power x. So this has even the 10th derivative will exist, 100th derivative will exist, even the infinite derivatives. You can keep on taking derivatives for this function. You'll get the same expression e power x again and again. Okay, so this is what higher order derivatives mean. But one thing I would like to mention here. Okay, just a second. Okay, so I think this is okay, right? So derivative as a function and higher order derivatives also, I just discussed everything here. Okay, so one thing I wanted to mention is this function we took, right? So f of x is equals to the first example, x power 5 minus 3x cube. So what kind of function is this? Is this even or odd?
Even function.
Again,
No,
think
sir.
about
I
it.
think odd function. Sorry, odd function.
Odd function, right? So this f of x is odd. When I take the derivative of this function, what is happening? 5x power 4 minus 9x square. Now, what is happening to f prime of x function? Is it again the same question, even or odd?
Even.
Even function. Now it's even, sir.
Even, right? So you see, if your f, the function is an odd function, then when you take the derivative, what will happen to the derivative? It will not have the same property. The property will be changed. If it is even, it comes to odd. Now, if I take the derivative once again, so if I take the derivative of even function, f double prime, what will happen to this? 20x cube minus 18x. Now, again, the same question. Is this even or odd?
Odd.
It's odd, sir.
Correct. So, what is happening is, now you can see a pattern, right? So, if you take an odd function and you see the derivative of it, the derivative function will become even. If you take an even function and look at the derivative of that even function, it will become odd. What if I take a neither odd nor even kind of function? What will happen to it? So let's say g of x, I have taken it as x cube minus x square. So x cube minus x square is neither even nor odd, right? So it won't satisfy any of the conditions. What will happen to g prime of x? And compute g prime of x and c. So this is neither even nor odd. And compute g prime of x and see whether it is even or odd. Okay, so I will leave it for you to think about, and you can get your answers. Okay. Okay, so but this is one good observation. So what is the connection between the function and its derivative function? Okay, so what is the property? Will the properties hold? All right, so let's move and let's quickly discuss the differentiation rules. Okay, so let's say f prime of x and g prime of x exists. Okay, once these two exist, then we can use this sum rule, right? So this is the sum rule, where if I take the summation of these two functions f plus g and look at its derivative, it will just be derivative of the sum. That's it. And the second thing is product rule, which says when I consider the product of these two functions derivative, fg's derivative, it will be f prime of x. You take the derivative of the first function, multiply it with the second function, add it to, take the first function and take derivative, multiply the derivative of the second function, right? So that is product rule. And I am very, very sure that even after discussing it many times in exam, some of you will just simply do f prime of x times g prime of x. So they will just simply do products derivative will be derivative of products, product of derivatives. Okay, which is not correct, right? So don't fall or don't do these silly mistakes. Okay, so the third property is division rule, which is like same as the second property, but this time we are dividing one function with another function. So f by g's derivative of derivative will be g of x into f prime of x minus g prime of x into f of x divided by g of x whole square. So if you forgot this formula, think of it like f is one function and 1 by g is the another function. Okay, so it is product of f and 1 by g. And you know, product rule is easy to remember, right? So you use product rule on f and 1 by g. That's it. You will arrive this particular formula. But this formula is also very not difficult to remember, right? And the last one, one of the important rules, which is composite rule, where we take composition of two functions, f of g of x derivative. This will become you have to take the derivative of the first function, keeping the inside function as is, and then multiply it with taking the derivative function of the inside one. So f prime of g of x into g prime of x. Okay, so that's composite rule. Okay, so these are the 4 important differentiation rules that you have to remember. Okay, now let's do bunch of examples. Okay, so let's say we have f of x is x and g of x is 2 by x. Now what we have to find is, we have to find the sum derivatives, so you compute the sum function and take the derivative and evaluate it at 0.2, and also f prime g, f into g whole prime of 2. Okay, so this is, we'll start with this fg's derivative of 2. If you use the formula, this is like you have to compute f prime of 2 into g of 2 plus g prime of 2 into f of 2, right? So if you have to do this, but you can do this in better way, where you see this f of x and g of x. When you take the product, what are we doing? We are multiplying x with 2 by x, right? So fg function will simply be f of x into g of x, or fg of x will simply be 2, a constant function, right? And when I take the derivative of the constant, what will happen? What is the derivative of a constant function?
0.
0, right? Even so, the derivative at any point will be 0. So at point 2 also it will be 0, right? At point 2 also it will be 0. So this way you can do. So sometimes you just have to stare at the question. Okay, just take some 10-15 seconds. Don't straight away looking at the functions and whatever is asked, don't use direct formulas, or don't sit on solving. Okay, so just stare at the question 10 seconds. Is there any other better approaches that I can do, or should I go with the formula? So just 10 to 15, after reading the question, 10 to 15 seconds of thought needed. Okay, so give that and then decide which method you wanted to use. So even this way also you can do. I'm not saying you will not get 0 if you do this way. You will get 0 only, but you have to compute g of 2. You have to compute f prime of x, which is, so f prime of x will be 1, and g prime of x, if you do, you will get it is 2 times x power minus 1. So if you take the derivative, you will see that you will get 2 minus 2 by x square, right? So now you can plug in the values of x is equals to 2 in these 4 formulas, and then do the computation. You will finally arrive to 0. Okay, all right, so this is 0. Now this we have to find. For this you can write this as f prime of 2 plus g prime of 2. So as we have just written down what is f prime of x and g prime of x, you can write it. So f prime of 2 will be 1 plus g prime of 2 will be minus 2 by 2 square. So this will be 1 minus 2 by 4, which is 1 minus half, which will be half. Okay, so that is how you can compute the derivatives of a newly defined functions, which are sum or product or whatever. Now let's go to the, yeah.
Sir, if fx and gx have a polynomial function, then we go through this formula or we can try different method.
If both are polynomials, then if you do the product, it will again give you a new polynomial, right?
Yes, that's the problem, sir.
then it depends on the polynomial length of the polynomial you have. If your f of x has some 5 terms and your g of x has some 6 terms, when you sit and do the product, it will take more time, no? So that is what you have to assess. Within that 10-15 seconds, when you see what if I take the product directly, what will happen? Okay, so I have 5 terms here, 6 terms here. If I do product, each term wise product I have to do, I will get somewhat 30 terms, which is hectic, right? Which is time consuming.
Yes. Yes, sir.
Then you have to decide that, okay, let's not do in that way. It's better to take the derivative of the first function separately, second function separately, and then evaluate at the point is much easier, right?
Or
So,
sir, we can differentiate and cancel the constant. So we have
huh,
the sorted polynomial represented by the graph.
uh, what do you mean by representing by the graph?
Like a sir, polynomial. Let's polynomial gx is x cube plus 4 by 3x square plus 5x. So we can differentiate the 5, double differentiate, then 5 is cancelled. So we have
No, that
two
is what. See that these
variables. Then
things I understand. So these things you have to decide during the exam. Okay. So it's not that there is
okay,
one
sir.
unique way to every problem. So it depends on the problem. So for that, after seeing the problem, you should choose what all methods. If you know 3-4 kinds of varieties, you should choose the best one. So for that, you need that 10-15 seconds. Think and you have to choose which one is the best one. Okay. So if you don't know anything, then you just have to use the formula. That's it. No other way.
Got it, sir. Continue,
Yeah.
please.
Yeah. All right. So let's do the second problem. Now what is the information given is these four. So f of 1 is 2, g of 2 is 1, f prime of 1 is -5, g prime of 2 is 4. What we have to find is this. So we know this is like compositions derivatives in both cases. So we'll write down. So this is g of f of 1's whole derivative. Right. So this is g prime of f of 1 and then f prime of 1. Right. Using the composition rule, we'll get this. And again, f of g of 2 whole derivative is f prime of g of 2 into g prime of 2. That's it. So we know what is f of 1 is. Substitute. You know what is g of 2 is. And also we know what is f prime of 1 and what is g prime of 2. So substitute them and you will see that this will become g prime of f of 1 is 2 into f prime of 1 is -5. Here f prime of g of 2 you go and see it is f prime of g of 2 is again 1 into g prime of 2 is 4. Okay, now g prime of 2 again is 4. So this will just become 4 into -5. And f prime of 1 is -5. So this is -5 into 4. Okay, so now what I have to do? Both are -20s. If I subtract both of them, it will give me 0. So this minus this is 20 minus 20 minus -20, which will give me 0. Okay, so that is how we can solve this. Now let's solve one more problem related to these derivatives and all, and we'll close the derivatives part here. Okay, so this is one of your activity questions, if I'm not wrong. So you have a function given to you such that it satisfies some condition. So f of x plus y is equals to f of x into f of y. Okay, and it is true for all x comma y belongs to real numbers. And you have we are also given that f of 9 is 3, f prime of 0 is 8. What they want is they want find the value of f prime of 9. Okay, so that is what they want. So how do we solve this? So there are many approaches, out of which this approach I found it really simple, which is firstly, if I want f prime of 9, I'll write the actual definition. What is the actual definition? I want limit h tends to 0, f of 9 plus h minus f of 9 divided by h. Right, so this is what I want to find. I know f of 9, right? But I don't know how the function is not given to me explicitly. So I was given f of 9 plus h, but I know when I add to f of x plus y is I can write it as f of x into f of y. So that I will use. So I am using, so let's say this is the condition 1. So this I am writing it as limit h tends to 0. This f of 9 plus h, I am going to write it as f of 9 into f of h minus f of 9 divided by h. So how am I writing? Using condition 1, I can write f of 9 plus h as f of 9 into f of h. Right, I can do this. Now if I pull out f of 9 out from the numerator, what will I have? I will have limit h tends to 0, f of h minus 1 divided by h. Okay. So what is this looking like? So we have something limit h tends to 0, f of h minus 1 by h. And another information is given to us. We didn't yet used it. So what is that information? It is this information. F prime of 0 to be 8. Right. So this information somehow I have to use. So for that, I have to closely look into this expression limit h tends to 0, f of h minus 1 divided by h. So if I have to connect this to somehow connect this to f prime of 0, I should know how f prime of 0 is defined in terms of limits, right? So all I am doing is I have to use the information that are given. That's it. So somehow I have to connect this with f prime of 0 so that I can get to the answer, get towards the answer. Okay. So now f prime of 0, if I have to define using the limit definition, I would have defined it like this. H tends to 0. F of 0 plus h, which is f of h, minus f of 0 divided by h. So if we see, we are very close to f prime of 0, but there is one difference between this and this. That is, here we have 1, here we have f of 0. Okay, so that's the difference. So again, that means I need to compute f of 0. So can I compute f of 0? So if I can compute f of 0 and see that f of 0 is 1, then I can simply say this is nothing but f prime of 0. Right? So all I have to check now. So can I get f of 0 is the question. And for that, so our mini goal is to find f of 0. How can I find f of 0? How can I find? We have this expression again. We'll go back to this expression. F of x plus y is f of x, f of y. Okay, so we substitute one variable x or y to be 0. So substitute x is equals to 0. Okay, so just substitute x is equals to 0. What will you get? F of y is equals to f of 0 into f of y. Right? So this is what we get when you substitute x is equals to 0. And what you are seeing is f of y is equals to f of 0 into f of y. So this is holding true for any y. So now I simply substitute because I know f of 9. I'll substitute y is equals to 9. if I substitute that, I'll have f of 9 is equals to f of 0 into f of 9. So I know that f of 9 is non-zero and it is equals to 3. I can cancel it out on both sides. Right? So all these are manipulation, that's it. So we started with computing what is required. F prime of 9 is required. Right? We started with that. We have written the limit definition. Then using this particular condition, we have breakdown into here. We have got f of 9, which we know, but we have arrived into some other limit. Okay. Then we went back to the question and saw, is there any information that I can use? So there is again an information on f prime of 0 is given to us. So that means this is somehow related to f prime of 0. Right? I saw what is f prime of 0. And f prime of 0 can be expressed like this. So this is very close to this, except here I have 1, here I have f of 0. That's the only difference. Now finding f of 0 is important now. How can I find f of 0? So I have this expression, and using again these informations, I have found that f of 0 is indeed 1. So once f of 0 is indeed 1, this and this are the same. Right? So that means this is simply f prime of 0. Okay. So what we eventually got is, we wanted to find f prime of 9, but this f prime of 9 is f of 9 into this another limit h tends to 0, f of h minus 1 divided by h. Now what we write is f of 9 into limit h tends to 0, f of 0 plus h minus, instead of 1 I am going to write f of 0, because f of 0 is 1. Right? So now this is f prime of 0. Right? So simply this will become f of 9 into f prime of 0. If I just substitute the values, f of 9 is given to be 3, f prime of 0 is given to be 8. We will get f prime of 9 to be 24. Okay. So what happened eventually? If we were asked you to find f prime of 9, it is just the product of this and this. Right? So we got that. That is how we have to solve this particular problem. So every problem you have to go towards the solution. Okay, so our ultimate goal is to find f prime of 9 using these three conditions given to us. Okay, so you have to use it somehow and get to the solution. And this is how I have used. And again, having said all of this, there are many different ways also you would have solved this. But ultimately, the answer should come out to be the product of f of 9 and f prime of 0. Okay, is this clear? I think these examples are sufficient. Solve more problems related to these particular concepts that we discussed till now. Okay, so that will cover derivatives. Now let's move to the next topic, which is the linear approximations and quadratic approximations. Okay, so the linear approximation L of x for any function f of x. Okay, please repeat f of 0 part. Okay, so f of f of 0. Okay, how many of you didn't understand this f of 0 part? Can you just raise your hands? Okay, so everybody understood, is it? Okay, 1, 2. Okay, fine. So the thing is, all right, so we have f of x plus y is f of x into f of y, right? And this is holding true for any x comma y belongs to real. So it will hold true for any xy. So what I did simply is, since it is true for any x and y, I just put x is equals to 0 and y is equals to 9. Because I know the informations of those values. So f of 9 I know. Right? And I want f of 0. F of 9 I know, I want f of 0. So I'm just using f of 9 find f of 0. So when I put these values in this expression, what will I have? On the left side, I will have 0 plus 9 is equals to f of 0 into f of 9. Right? So this will become f of 9 is equals to f of 0 into f of 9. So f of 9 is 3. I know that. If you substitute 3 is equals to f of 0 into 3. Right? So what should be f of 0 then? F of 0 will simply be 1. Okay. I hope this is okay then. So instead of 1, I wrote f of 0, and that is exactly f prime of 0's definition. It will just become f prime of 0.
But sir, in this like f of 0 will be 0 now, like, because this is in subtraction, not in multiplication.
Which is in subtraction, that is multiplication, no?
Oh, this is in multiple. Oh, okay.
So here it is multiplication, no? F of x. So the given information is f of x plus y is f of x into f of y. That is into. That is not y. Minus. Okay.
Okay, sir. Okay.
Oh,
That was my mistake.
okay. So that is product. All right. So let's move ahead. Let's talk about linear approximations. So the linear approximation L of x is a function. And this function approximates the function f of x around some point x is equals to x naught, and is given by L of x is equals to f of x naught, the function value at the point, plus the derivative value at that point into x minus x naught. So that's the formula. Okay, so this is the formula, and we have derived this in earlier live sessions. I don't want to derive it again, but this is the formula, we will use it. Okay, so given example here, f of x is given to be x square minus 1 by x plus 1. Find L of x around x is equals to 0. So this is important to us. Okay, so here x naught, you can see this is x naught. Right? If I write the linear approximation formula, L of x will be f of 0 plus f prime of 0 of x minus 0, because x naught is 0 here. So we are interested to find the linear approximation around x is equals to 0. Okay, so now you can see f of 0 is a constant, right? So this is a constant. Once you know x naught, f of x naught is just a constant. So this is also a constant. The only variable is this x, and that is linear, right? So everything is constant, and we have a constant plus some constant multiplying by x, which is like a straight line function, straight line equation. So that is why it is linear approximation. Okay, so here also f of 0 we can find, f prime of 0 we can find. Both we can find. Right. Yes.
Sir, linear approximation formula is not working in periodic function. Why?
Linear approximation is not working in periodic. Why? It will work, no?
Yes, sir. Not working
See
in
this.
periodic functions like sine 1 by x. If fx is equal to sine 1 by x.
It will not exist. See, sine 1 by x when x is equals to 0 is not defined, right? So firstly, your function should exist at x is equals to x naught. Then you can get the linear approximation. Okay.
Okay,
So sine
okay,
x is a periodic function, right? Sine x. You know sine x is a
yes,
periodic.
sir.
Sine x at x is equals to 0, you can get a linear approximation.
Okay, at x is equal to 0, we got. Okay, sir. Thank you.
You can find. At x is equals to, at any point, you can find linear approximation for sine x. Okay, so it's not necessary that periodic functions will not have linear approximations. It is not the correct statement. Okay, so our function should be properly defined at x is equals to that x naught point. Properly defined means you should know all the information, like you should know f of 0, you should know f prime of 0 also. Okay, it should also exist. Likewise, f double prime, f triple prime, Everything should exist. So here in this case, we have f of x to be like this. So f of 0 is 0 square minus 1 by 0 plus 1. Right? So f of 0 is simply minus 1. And we can also find f prime of 0. F prime of 0, that is also required. For that, we need f prime of x. So when I compute f prime of x, I will get it is 2x, x square derivative 2x, and minus 1 by x derivative will be so again you should know how to take the derivative, compute the derivative of 1 by x plus 1. Okay, it is minus 1 by x plus 1 whole square. Okay, I hope I'm taking into consideration that you know these derivatives, how to compute. This will be the derivative. And here f prime of 0 will simply be substitute 0. And you will see that it is 1. And this is also required for us. You bring these two and substitute here. That's it. So f of 0 is minus 1 plus f prime of 0 is 1 times x. This is simply x minus 1. So our L of x is simply x minus 1. And if I ask you to compute L of 2, will be 2 minus 1, which is 1. So like this, once you have L of x with you, it's just a function. And I can ask anything, right? I can ask you to compute L of 0.2. L of 0.2 is 0.2 minus 1. So whatever you get, you just have to subtract by minus 1. Right? So getting this is the difficult part. So how can I get this? I need to compute the function value at that point and its derivative value at that point. So only these two things are required for me. Okay, so that is for linear approximation. So I can also do quadratic approximation. So the only difference between linear approximation and quadratic approximation is quadratic approximation will have one more term. Okay, so this is the new term. And this term will have x square coming into the picture. So that is why this is quadratic approximation. You will have x square term, x term, and a constant term. Okay. So even here also, this is constant. This is constant. This is constant. Because once you know x naught point, you can actually compute them. Right. This is also constant. So the only variables are x here. Right. So this x is a variable. This x here is a variable. Okay. So for this, quadratic approximations are better than linear approximations, but the cost is you have to compute more. So the computational cost is higher. So in linear, you just have to compute this and this. But in quadratic, you also have to compute the double derivative at that particular point. So for example, again, you have the same function. Okay, so for this, we already know f of 0 is minus 1. F prime of 0 is 1. Right? So we also have f prime of x, which is 2x plus 1 by x plus 1 whole square. Right? So we will use this to compute f double prime of 0. So we need f double prime of 0 now. Right? Right? Is everybody getting this? So we have to get this term now. So that is f double prime of 0. So for that I need f double prime of x first. So for f double prime, second derivative of x, I have to take the derivative of the first derivative. I will get the second derivative. If I take the derivative, I will have 2 plus 2x derivative is 2. 1 by x plus 1 whole square derivative will be minus 2 by x plus 1 whole cube. Again, this also, you just go back, practice. You will see that this will be 2 plus minus 2 by x plus 1 whole cube. Now what I have to do? I need f double prime of 0. I just have to substitute 0. I will see that this is 0. Right? So that means Even the quadratic approximation and the linear approximation both are same in this particular case. So sometimes you may not get 0. So you may get something like, let's say this is, you got +2. Okay, so here it is not, you got +2, this will become 4. So if you got some non-zero value, then what happens is you will have your quadratic approximation to be f of 0 plus f prime of 0 into x minus 0 plus f double prime of 0 divided by 2 factorial x minus 0 whole square. Okay, so now f of 0 is -1 plus 1 times x plus this is 4 divided by 2 factorial. So don't forget this 2 factorial. Okay, so you will do all the things, but if you forget this 2 factorial, then again you will go wrong. Okay, so this is x square, and this is how the expression look. But here in this case, in our case, it happened to be 0. Once this is 0, here it is 0, and this term will go to 0. Again, we'll get the same thing, which is x minus 1, which is actually the linear approximation. So even though you are going higher approximations, it is not improving. Your approximation is not improving. So that means your function, this x is, so this x square minus 1 by x plus 1 around 0 is actually behaving like a straight line. It is almost like a straight line. So even if you take a quadratic approximation, it will do a straight line approximation only. So no major difference. Okay. But for other examples, this will change. Okay. So that is about linear approximation and quadratic approximation. And this is really important. Given a function to you, around a particular point, you should be able to compute the linear approximations and quadratic approximation. There are bunch of problems sitting in activity and practice and graded assignments. Okay. So go practice and get used to this. So how do you find the linear approximations and quadratic approximations? Okay. So this summarizes week 5. We will just take a 4-minute short break just to refresh ourselves. So I agree that continuous 2 hours will be like a hectic. Okay. So just have some water and come back by 5. We will discuss week 6. Okay. Yeah. All right, so hope everybody is back. So we will start week 6 now. Okay. Are you guys back? Hello? Nobody came back, huh?
Yes, sir, you are audible.
Yeah, I'm audible, right? So you are all back, no? Had cool drinks? Okay. So by the way, cool drinks are not good for health. And I am not going to preach you, but it's good that you avoid them. All right. So let's begin with week 6. And one of the most important concept that you have to learn is you should know how to compute the local maxima and local minima. And we can use the power of derivatives to kind of conclude whether the given or actually can compute where the point uh, sorry, at which point we get a local maxima, at which point we get a local minima of any given function. But before that, we should know what are local maxima and local minimas of any given function. So if the curve is given like this, so this is f of x, the black curve, and you have some very special points. I have plotted them also. So x1, x0, x1, x2, x3, x4. Okay, so these are special because when you look at the graph, okay, so at x0, you see at x0. So the left of x0 and the right of x0, both are below this point. So this looks like a peak point, right? And mathematically also, if you see, till that point, my function value is increasing. And after that point, my function value is decreasing. So the function property, one of the property like increasing, decreasing will change at that particular point. Similarly, at x1 also, it is decreasing and then increasing. So x1 is like a bottommost point. So here also increasing became decreasing. Here decreasing became increasing. Again, here increasing became decreasing. Okay, so these are special in that way. Now, what are local maximas and local minimas are? Local maximas are the points where the function attains maximum value around a small interval. So something like this. So this x0 point is a local maxima because anything left of x0, anything right of x0, the function value is lesser than f of x0. So this is a local maxima. Similarly, x0 is one of the local maxima. Even at x2 also, if you see, left of x2 and right of x2, both function values are lesser than f of x2. So even this also is a local maximum. Similarly, this is also a local maximum. Right? So these points, peak points, are the local maximas. Whereas these points are local minima. Again, what is local minima? So the function attains the minimum value around that small interval. You can see here. So if you move right of x3 or left of x3, the function value will increase. F of x3 is the minimum value compared in this interval. And even at x1 also the same condition holds. Okay, so these are local maximas and local minimas. Now if I have to conclude whether a given point is a local maxima or local minima, how can I do it mathematically? So graphically I can see, right? So given a graph to me, I can say these are the three different points where function attains its local maxima. These are the three different points where function attains its local minima. But if graph is not given to me, only the function, the analytical expression is given to me, mathematical expression. Then how can I find? So from the graph itself, you can see you can see that at these special points, if I compute the slope or the derivative value, okay, so if I compute the derivative value, it will be 0. Right? You compute all these 5 points, you compute the derivative value, it will give me 0. So what do I mean by that? So it is like, if I compute f prime of x naught, if I compute f prime of x1, if I compute f prime of x2, and so on, if I compute f prime of x4, so all will be equals to 0. So first and foremost condition is, whether it is local minima or local maxima, f prime or the derivative value at that point should be 0 first of all. Okay. And the next condition is, you see the slopes actually increase and then comes to 0. Right. So the function is increasing, but the thing is, when you see the derivative values will decrease and then increase. Right. So in other words, if I compute f double prime of that point, okay, the second derivative at that point, if it is less than 0, okay, if it is less than 0, then we call it as local maxima point. And if the double derivative value is greater than 0, we call it as local minima point. Okay, so you have to check two conditions. First and foremost condition is, the first derivative should be 0. Okay, so the first derivative should be 0. Then once you compute the first derivatives and equate it to 0, you will get some points. So those points are your critical points. Okay, so special points. Now among these special points, which are local maxima and which are local minima, that will be decided by the second condition, which is checking the double derivative. If your double derivative value at that point is greater than 0, it will be local minima. If it is less than 0, it will be local maxima. Okay, so we'll solve a problem and then we will get a complete understanding. Okay, so given a function like this to me, okay, f of x is 3x power 4 plus 2x cube minus 17x square plus 90x minus 60. So what we have to find is, we have to find the local maxima and local minima. Okay, so for that, the first step 1, or checking the condition 1. So my f prime of x should be 0. Right, so then I can say x is a special point. Right, so for all the x such that f prime of x is 0, then they are special. Right, so that means I have to solve for f prime of x is equals to 0. So how can I do this? I have to compute f prime of x first. Right, so f prime of x, if I compute f prime of x, that will be 12x cube plus 6x square minus 34x plus 90. Right, so this is the derivative, and what are the critical points? So I have to equate it to 0. Now how can I solve this cubic polynomial? So sometimes cubic polynomial, for cubic polynomials, you have to guess the first root. Okay, you just have to substitute x is equals to 0, then x is equals to 1, x is equals to minus 1, x is equals to 2, x is equals to minus 2, and so on. If we are lucky, then we might get our first root to be one of these 5 points. Okay. Here What is happening here? So can we do something? F prime of 0. F prime of 0 will never be 0. That is okay. If you check f prime of -1, will it give 0? No. F prime of 1 will not give 0. F prime of 2 will F prime of 2 give me 0? So for F prime of 2 also will not give me 0, but F prime of -2 is 12 times -8 plus 6 into -4 minus 34 into -2 plus 90. So what will this give me? So 12 eighths is -96 minus 24 plus
Plus 4
68
here.
plus 90. Sorry?
6 into plus 4 is square, x square.
Ah, that is plus 4. Sorry. So this
Yeah,
is plus
minus 0.
24. It is not giving us 0, right? Okay, I messed it up. I think my calculations are wrong. So let's say, so instead of this, I'll do one thing. Let's forget about f of x to design f of x. Let's say you have directly f prime of x. Okay. So f prime of x to be given like this, x into x minus 1 into x plus 1. Okay, so consider a function such that its derivative itself is given to you. Okay, so now you have to find the local maxima and local minima. Okay, so let's do this one. So once you have f prime of x to you, then if you equate it to 0, x into x minus 1 into x plus 1 is equals to 0. Now I can get the roots easily, right? So from here I can see that when x is 0 or when x is 1 or when x is minus 1, right? So this is clear, right? So if f prime of x itself is given to us, then we equate it to 0 and see at what points the first derivative is being 0. And at these 3 points, the first derivative is becoming 0. Yes, Sudhanshu?
Sir, is it only one way to check the local maxima and minima? Because sir, if the function will never be zero, then how can we calculate the local maxima and
Then there will not be any local maximum or local minimum.
oh,
Yeah. So if
so
it is a
so,
local
sir,
minima,
sir,
yeah.
for the previous equation, I
Hmm.
mean function, can we say that there will be no any local maxima and minima?
No, no, it will be no. So it will be 0. F prime of x will be 0 for some values, but
Okay,
it will not be an integer. You can plot and see, no? I think I have made some mistake there.
okay, sir.
Okay. So okay. Okay, so that's a mistake. Okay, so when you take f prime of x, you can go ahead and plot this f prime of x in Desmos, and you will see there will be some roots, which will not be integers. That's it. Okay, so let's say f prime of x. So let's not take the burden, no. So let's say f of x is given to you, and then we computed f prime of x, and f prime of x is looking like this: x into x minus 1 into x plus 1. So now, how can I compute the local minima or local maxima? So, or how can I use these conditions? Okay, so the first condition is I will equate it to 0 and find the critical points, special points first. So these are the special points, right? So once you have the special points, the second thing is you have to check the signs of f double prime of 0, f double prime of 1, and f double prime of minus 1. Okay. So for that, you have to take the derivative of this function. Okay. And this is x cube minus x, right? F prime of x is simply x cube minus x. If you multiply all three, you will see that it is x cube minus x. And if you take the derivative, f double prime of x will be 3x square minus 1. So this is f double prime of x. When I substitute x is equals to 0, I will have -1, which is less than 0. And we will have f double prime of 1 to be 3 minus 1, which is 2, which is greater than 0. Similarly, for -1, we will have -3 minus 1, which is -4. Therefore, this is less than 0. So from here, I can conclude that 0 is local maxima and 1 is local minima and -1 is local maxima of f of x, not f prime of x. Okay, so even though f prime of x is given to us, so this local maxima, local minima points are for the function f of x. Okay, so don't plot f prime of x. If you plot f prime of x, you will see that at x is equals to 0, x is equals to 1 and x is equals to -1, it will cut x-axis. It will intersect x-axis. Okay, they will not be the local maximas for f prime of x. They will be the local maxima and local minima of f of x only. But this is how you should check. Firstly, you should find the roots of f prime of x is equals to 0. And once you get the roots, those roots are your special points. So they will be either local maxima or local minima. In order to conclude which one is local maxima and which one is local minima, you have to compute f double prime at those points and see if it is less than 0, it will be local maxima. If it is greater than 0, it will be local minima. Okay? Is this okay? Nice.
Yes.
Now let's talk about Rolle's theorem and mean value theorem together. Okay, so I don't have any example also, but solve problems, some problems, word problems related to Rolle's theorem and mean value theorem. So what is Rolle's theorem? If you have a continuous and differentiable function in the interval AB with the condition that f of A is equals to f of B. Okay, so you know that it is your function is continuous and differentiable in the interval AB, and also you know that f of A is equals to f of B. Then what can we say is there exists a point C in between AB such that the derivative will be 0. Okay, so graphically, what does it mean is you have your function. Okay, so the right of B and left of B, you don't have to worry, it can behave anyway. It can, but all that we have to worry is in this interval A to B, and you know that it is continuous and differentiable. If it is continuous and differentiable, it has to be smooth. So something like this, or something like this, something like this, right? So if you consider anything, any smooth curve that connects A to B, so if it is going above, then it has to reach back B, right? It has to come back to B. So that means there should be a peak point. Or if it is going below of f of A, then it has to come back to f of B again. So that means there should be a turning. So if there is a turning, then at that point slope will be 0. So that is what Rolle's theorem says. So you consider any smooth connection, there will always exist a point such that slope at that particular point is 0. And which is graphically also makes sense, right? So if it is going, you know that f of A and f of B should be equal. So they have the same value. If you go above that value, you have to come back to that value. If you go below that value, you have to come back to that value again. So there should always exist a turning. So that is what Rolle's theorem says. And what does mean value theorem is? It is just the extension of Rolle's theorem, which is you don't have this condition. Your f of A may not be equals to f of B. Okay, so it can be different also. Okay, so in that case, what can I conclude? Okay, so if the same conditions, f is continuous differentiable in AB, then there exists C such that f of B minus f of A divided by B minus A is actually f prime of C. Okay, so there exists a point C such that the difference between the function value divided by b minus a. So what is this actually is, you construct a straight line passing through a comma f of a and b comma f of b. Okay, so if I consider a straight line that passes through these 2 points, then what is the slope of this straight line? Can anybody tell? So you know this straight line passes through a comma f of a and b comma f of b. So you know 2 points on the straight line,
FB minus FA upon B minus
fb upon f of b minus f of a divided by b minus a, which is what the right side you are seeing. Right, the slope is actually this, f of b minus f of a divided by b minus a. Now what does this mean value theorem says is, now however you connect this a comma f of a and b comma f of b, it should be smooth connection. So it can be like this, like this, like this, like this. So it should be very smooth. Okay, so however you connect, there will always exist. Okay, so there will always exist a point C, such that when I compute the slope at that particular point, that will be same as this slope. So the slope of the line connecting a comma f of a and b comma f of b. And again, graphically also it makes sense. So they both will be parallel. Parallel lines have the same slope, right? So there will always exist a point. So that is what mean value theorem says. Okay, so the average value over this interval is f of b minus f of a divided by b minus a. So the average value should be attained at one particular point, right? So if you're traveling in a car and you start from 0 and you have reached 100 kilometers per hour, and again you have traveled with different speeds throughout, and finally you arrive at one point, another point, right? So and you see your average time that you took, or the average speed with which you traveled, it can be some 60 or 63. So at some point you would have touched 63. That's what mean value theorem says. Okay, so that's about mean value theorem. I don't have any problems specially on this, but you can solve problems from activity and practice graded. Okay, so the next concept is L'Hopital rule. So L'Hopital rule is again which will help us to compute limits. Okay, when we were not able to do limit computations when we arrive something of the form 0 by 0 or infinity by infinity, which are called indeterminate forms, right? So when we reach these kind of expressions, then we don't have any tool to compute the limits further, right? So this L'Hopital will help us. So how does it help us? If f of x naught divided by g of x naught is approaching to some indeterminate form 0 by 0, so and you are interested to compute limit extends to x naught f of x by g of x, since this is taking you to 0 by 0 form, so what you can do is, this L'Hopital says is, you take the derivative of the numerator, derivative of the denominator, and compute the limit as x tends to x naught. It will give the same value as this. Okay, so that is what L'Hopital says. And another advantage of L'Hopital is, or another property of L'Hopital is, you can use it multiple times. Let's say if you got 0 by 0 again, what you can do is, you can again use L'Hopital and say, this is same as limit x tends to x naught f double prime of x divided by g double prime of x, right? But only on one condition. You should always be very, very careful when you are using L'Hopital. So the previous expression should give you 0 by 0 or infinity by infinity. Okay. If it is giving you something like 1 by 0 or infinity by some real number, infinity by some 10, if it is giving that expression, they are not indeterminate forms. So you cannot use L'Hopital blindly. Okay, so to reduce your expression, you should not use L'Hopital continuously on numerator and denominator to get a constant in the numerator and constant in the denominator. You cannot do that. Okay, so L'Hopital only works when your previous expression is giving you 0 by 0. So only if this gives 0 by 0 form, only then you have to take the derivative of the numerator and derivative of the denominator. And even after that you are getting 0 by 0, only then you can use this. Okay, so that be careful about that. So let's do these problems quickly. Yes.
Sir, I have a question. L'Hopital's rule is basically applied in sequence and series. So,
It yeah, yeah. So you finish your question.
so in Taylor expansion, L'Hopital's is best option or not?
In Taylor approximations.
Taylor expansion,
Okay, Taylor
like
expansion.
EX minus 1. Yes, sir.
So e power x kind of expressions.
Yes, sir. Yes, sir.
Okay. So there also. mm, okay, if you use L'Hopital again and again, you might end up in the loop. Is that what you are saying? You're asking something
Yes,
like
yes.
if
L'Hopital's
you
is
take
infinite.
so in those cases, na, you have to be really careful. So if you are taking e power x in the numerator and you constantly take the derivatives, okay, and you will end
Sir,
up getting e
then the
power x only.
denominator will be, yes, sir. Then the denominator will be 0, and then we put the limit so it's get answer 0. Okay, sir, I got it.
It will. So if the denominator is just a polynomial, after certain derivative, after certain times you use limit L'Hopital, you will see that eventually the denominator will become constant, but the numerator will be infinite. So that will give you infinite.
Okay, sir.
Okay. Yeah. Okay. So let's solve this problem. So you see, limit extends to 0, x cube by e power x square minus 1. So when you try to substitute 0, you will see that you will end up getting 0 by 0 form. So you will see that you will get 0 by 1 minus 1, which is an indeterminate form. So what you can do is you can take the derivative of the numerator and derivative of the denominator. And this is equals to derivative of the numerator is 3x square divided by the derivative of the denominator is, it's a composition of two functions. So if you compute the derivative, you will see that it is 2x into e power x square. Okay. And this x will cancel and you will have limit x tends to 0, 3x by 2 into e power x square. So can I again use L'Hopital or should I again use L'Hopital here? So when you substitute x is equals to 0, now what will you get? The numerator will be 0. But what happens to the denominator? 2 times e power 0, which is 1. And this is a determinant value. So 0 by 1 or 3 times 0 is 0. 0 by 2. 0 by 2 will give us 0. Right? So this is a determinant value. So you should not take again the derivative once again in the numerator and denominator. Then you should not claim that this goes to infinite. So if you take L'Hopital once again, you will see that you will get 3 by 2 into 2x into e power x square. So x comes in the denominator and as x tends to 0, something by 0 will go to infinite. Okay, so be careful about that. So the answer for this is 0, not infinite. Yeah, somebody raised your hand. Okay, fine. So similarly, you can also compute this. So if you see, so for this we have used L'Hopital once and we got the answer. But for this, it requires a couple more steps. So when you try to substitute minus 2, you will see that the numerator and denominator will become 0. Right? So minus 8 plus 8 becomes 0 and minus 32 plus 32 becomes 0. So you'll get 0 by 0. You can use L'Hopital. So this will become 3x square divided by 5x power 4. Right? I can use L'Hopital once and I will get this. Now you can either cancel this terms out. Right? So this will become x square. Right? You just cancel, do the simplification, and then you will see that this will just become, again this also we have used only once. Okay. Anyway, so minus 2, this will become 3 by 5x square. And now you can substitute minus 2 and you will see that you will get 3 by 20. Okay, so this is how you compute the limits using L'Hopital. And L'Hopital is only, again, strong note. L'Hopital you can use only when you end up getting an indeterminate forms. Either 0 by 0 or infinity by infinity or infinity by minus infinity by infinity, these kind of forms. Okay. Only then you are supposed to use L'Hopital. Okay. That's it. So let's finally come to this Taylor's theorem for linear approximation and quadratic approximation. As I said, we will only be talking the Taylor series approximations for linear and quadratic, not beyond that. Okay. So the Taylor's theorem for linear approximation requires some conditions. Those are f and your f prime should be continuous in the interval a comma x. So the point A is the chosen point. Okay, so x is equals to A is the chosen point, and in the domain of a comma x, so the right interval in some sense. So a to x, my f and f prime should be continuous, and f double prime should exist. Okay, so these two conditions should be holding true. Then there exists a point. Okay, so there will always exist a point x2 in this interval a comma x, such that our function f of x is actually equal to, it's not an approximation. Okay, so we are writing it equal to, observe this. So we are not writing this. Okay, so this is approximation. What we are writing is f of x is equal to the linear approximation. So you'll have a linear approximation. So recall, just now we discussed, this is a linear approximation L of x, right? F of a plus, let me write, linear approximation L of x at x is equals to a. Okay, so this is the linear approximation. And we will have a new term f double prime, some point x2, such that if you add that, you will get f of x. Okay, and this term is referred to as error term. Okay, so when we do the linear approximation, we will have the value to be L of x, not f of x. So the difference between f of x and L of x is the error. F of x is the actual value. L of x is the approximated value, linear approximated value. And the difference, absolute difference between these two is the error. Actual minus the approximated value will give us the error. Right? So that is what it is. So absolute value of f of x minus this L of x, okay, is actually the error this. Now finding this x2 point is really difficult. Okay, so for that what we do is we say that this is anyway not dependent on the point x2. This 2 factorial is also not dependent on x2. So only this thing is dependent on x2, right? So f double prime of x2. So what we say is, let's say the maximum value. So what is the maximum possible value of f double prime of x2? Okay, so you compute the maximum value possible for f double prime of x2. And we say that the error will be the maximum. So the maximum error that is possible is when this f double prime of x2 takes a maximum value. Right? So that is why what we do is we bound this error, or we bound this modulus f of x minus L of x, saying this will never go beyond, or this will always be lesser than or equals to maximum value that this f double prime of x2 can attain. Okay, so maximum. So x2 in this interval a comma x, you compute the maximum possible value for f double prime of x2, and you multiply by x minus a whole square, and you just take the absolute value, because if you are getting negative, you just have to make it positive. So for that, you'll take the absolute. Okay, so what we say is the maximum, you compute the maximum error, and you know that maximum error is the maximum possible error, and anything apart from that, your error will always be lesser than that. And this f of x minus L of x is the error, and this will never cross maximum possible error, which is this. Okay, so when we ask you to compute or give us the maximum possible error, so what you have to do is you have to evaluate this expression, and you have to closely look into this f double prime of x2 function, f double prime of x function, and then try to get the maximum possible value for that expression, and then you substitute that maximum possible value here and get the maximum possible error. Okay, so we will do an example, and then we will get more clarity on this. Okay, so but before that, this is what Taylor's theorem for linear approximation is. So this is the linear approximation that you have to compute. That will be your linear approximation. And for error, what you have to do is you have to maximize this expression, which is f double prime of x2 divided by 2 factorial into x minus a whole square. Okay, so let's do a problem. Let's say f of x is ln x in the interval 1 comma e. So some of you would have seen week 9. So that is why I brought this ln x. I hope most of you know this, right? Is there anyone who doesn't know what ln x is? Log base ex. Okay, good. So in the interval 1 comma e, and f f is continuous, and this symbol c1 ex is that your f and the first derivative both are continuous in the interval e comma x. Okay, so we have given f of x in this interval, but we don't know how the function is behaving after e. That means e to some x we don't know. But what we know is f and f prime are continuous in that interval e comma x, and f double prime of x also exists in this interval e comma x. Now what I want is find a degree 1 polynomial L of x to approximate f of x in the interval e comma x. Okay, so that is what we wanted to do. So for that, this is nothing but the part 1 is nothing but asking you to compute the linear approximation to f of x, considering x naught to be e. Okay, so here you have ln x to be like this. So if you people who know the curve, this is how ln x will behave. And what we know is we know only till e. Right, so the graph from 1 to e, and after that we don't know. So we only know till here. This is e and this is 1. Okay, and now you are here. And now you are to approximate f of x. So we are trying to what happen or how will our function behaves to the right of e. Okay, so how does it will behave? Will it go like this, like this, like this, like this, or like this? How does it go? So for that, we are going to do an approximation, considering our x naught point to be this. You are here. And now what? How are we going to approximate? We are going to do a linear approximation. Okay, so x is equals to x naught. So here x naught is E. And what we have to do, we have to get a linear approximation around the point E. Okay, I hope this is clear. We are not considering at point 1, we are at point E. So we need linear approximation L of x at x naught is equals to E. So for that, we know the expression L of x is f of x naught is which is f of E plus f prime of E into x minus E. Right. So for that, we need f of E and f prime of E. Okay. So that we can get it. We know f of x is ln x. So f of E is ln E. Most of you would know this. Log E base E is 1. Right. We have f of E to be 1. We got this. Right. So this is equals to 1. Now we have to find f prime of E. For that, we need f prime of x. So f prime of x, when I take the derivative of ln x, it is 1 by x. Right. So f prime of E is 1 by E. Right. Even this also we got, which is 1 by E. Now putting everything together, we'll have 1 plus 1 by E times x minus E. And if I expand this, 1 plus 1 by Ex minus 1 by E times E will become 1. And this one and this one will get cancelled out. You will have simply x by E. Right. So our linear approximation is simply x by E. So once we have this L of x to be x by E, that is our degree 1 polynomial which approximates f of x in the interval E comma x. Now the next part is about using Taylor's theorem, find the maximum possible error in f of 2e minus L of 2e. Okay, so this is, we have to find f of 2e minus L of 2e's maximum possible error. And we know that the maximum possible error is max of some point x2 in the interval E comma x f double prime of x2 divided by 2 factorial x minus a. X minus the point that we are considering here is to E, sorry, E whole square. Right. So I have to find, so this is the maximum possible error. So I am interested in this particular thing. Right. So I have to get x2 and I should also get x. So for x, this is actually x, right? So f of x and L of x. Okay. So for f of 2e, max possible error, f of 2e minus L of 2e is max of x2 in the interval E comma 2e. So now x is 2e. F double prime of x2 divided by 2 factorial 2e minus e whole square. Right. So all I have to find is the maximum possible value for f double prime of x2. Or once I get f double prime of x, then I can talk about max value. Right. So I have f prime of x with me, which is 1 by x. Right. So f of x is ln x, f prime of x is 1 by x, and I can compute f double prime of x, which is minus 1 by x square. Right. So minus 1 by x square, and we are interested in absolute value. So absolute value of f double prime of x is absolute value of minus 1 by x square, which is absolute value of 1 by x square, which is 1 by x square. right? So 1 by x square is always positive. So now look at 1 by x square, and I have to find the maximum possible value for this in the interval e to 2e. Okay. So what could be the maximum possible error? So now again the mini goal is find the maximum value of f double prime of x, which is 1 by x square in the interval e to 2e. So we are interested only in the interval e to 2e. Now if you see 1 by x square, as x increases, 1 by x square value will decrease. Right? It's a decreasing function if you observe that. So in this interval, you can see that at x is equals to e, it has 1 by e square. But as x becomes greater than e, the value will reduce. It will not increase. So the if you plot the curve, you will see that. So this is f double prime of x with the value x. Okay, so absolute value. So you see that when x is e, you will have 1 by e square. Okay, and from there, the value will decrease, and finally when it reaches to 2e, you will observe that 1 by 2e square will be 1 by 4e square. Okay, so now within this interval, now we can clearly see that the max value will attain at this point, at the point e. So therefore, the maximum occurs at point e. Right, so what you have to do is x2 now is e. Right, that's it. So the max possible error is f double prime of e divided by 2 factorial into 2e minus e whole square. Okay, now x2 became e, that's it. Because at the point e, it attains the maximum value. Anything after e, the value is reducing. Okay, now I know f double prime, which is 1 by x square. So f double prime of e will be 1 by e square divided by 2 factorial. And this is 2e minus e, which is e square. Okay, now this and this will get cancelled out. You will have 1 by 2, which is the max possible error. Okay, so I think you would have solved many problems related to this, but it is always good to practice more problems on Taylor's theorem, and you will see that this is how we compute the max possible error. Okay, I hope this is okay. Now we will also quickly do Taylor's theorem for quadratic approximation. So for quadratic approximation, again, the first 3 terms will be your q of x, and the fourth error term will again be like f triple prime of x2 divided by 3 factorial into x minus a whole cube. Okay, so this will be the error term. And the max possible error is the maximum possible value that this can attain in the interval a comma x. Okay, so again the example is, okay, again the example is, you have f of x to be square root x plus x square by 2. You have to find the second order Taylor approximation for f around x is equals to 1. Okay, so when we say second order Taylor approximation for f around x is equals to 1, it means that we are asking you to compute the quadratic approximation, and then the error term will be f triple prime of x2 divided by 3 factorial into x minus a whole cube. Okay, so the same approach we follow. So we'll write down the q of x, second order Taylor's approximation. Okay, so which is q of x, which will be f of a plus f prime of a into x minus a plus f double prime of a divided by 2 factorial x minus a whole square, where a is 1 here. Okay, so we are interested in around x is equals to 1. So when I substitute a, I will have to compute f of 1, f prime of 1, f double prime of 1. So for that, I need to compute, before moving forward, you have to compute f prime of x, which is when you compute, you will see that this will be 1 by root 2x plus x. So root x is 1 by root 2x and x square by 2 is x. And again, you have to compute f double prime of x, which is minus 1 by 4 x power 3 by 2. Okay, so when you compute 1 by root 2x derivative, you will see that it will be minus 1 by 4 into x power 3 by 2 plus derivative of x is 1. Okay, so now you can actually get f of 1. F of 1 is simply 1 plus 1 by 2, which is 3 by 2. Right, so from here you can write f of 1 is 3 by 2. Similarly, f prime of 1 is 1 by 2 plus 1, which is again 3 by 2. Here f double prime of 1 will be minus 1 by 4 plus 1, which is 3 by 4. Okay, so once you have this, we can write down q of x, which is f of 1 plus f prime of 1 into x minus 1 plus f double prime of 1 divided by 2 factorial x minus 1 whole square. If you just simply have to substitute, so this is 3 by 2 plus 3 by 2 into x minus 1 plus f double prime of 1 is 3 by 4 by 2 factorial x minus 1 whole square. And you simplify this, you will get q of x. Okay. So once you get q of x, then the question could be like this. Right. So using Taylor's theorem, find an upper bound on f of 2 minus q of 2. As you know, the max value is max possible error is this. So upper bound will be this. Max of x2 belongs to a comma x, f triple prime of x2 divided by 3 factorial x minus a whole cube. Now a is 1 here, we know. So when we do that, when we substitute that, we will see that this is f triple prime of x2 divided by 3 factorial x minus 1 whole square, whole cube. Right? So absolute value. Now x is 2 here. So it will just become f of 2 minus q of 2 less than or equals to max of x2. I have to find a point in the interval 1 comma 2 such that f triple prime of x2 divided by 3 factorial into 2 minus 1 whole cube. Okay. So this is f of 2 minus q of 2 less than or equals to max of x2 belongs to 1 comma 2 f triple prime of x2 divided by 3 factorial, because 2 minus 1 whole cube is simply 1 cube, which is 1. Okay, so now we have to find f triple prime. So for that, we already have f double prime, which is minus 1 by 4 x power 3 by 2 plus 1. Okay. So f double prime of x. So all these things, I expect you should parallelly do these computations. Okay. So only when you put pen on paper, you will understand what exactly is happening. If you just see what I am writing, then you will get half of the things and you will not be able to understand the other half. X power 3 by 2 plus 1. Now from this, if I have to get f triple prime of x, this will give me 3 by 8 x power 5 by 2 plus 1's derivative is 0 anyway. Okay. So this is what we get. again, if you observe this 3 by 8 x power 5 by 2, again x is only in the denominator, and we have to find the maximum value in the interval. Maximum value in the interval 1 comma 2, right? So we are only interested in the interval 1 comma 2. So again, even here also you can see within 1 comma 2, f triple prime of 1 will attain the maximum, whereas when x increases, this value will decrease. So this is a decreasing function. So once you know that this is a decreasing function, then f triple prime of 1 is maximum. Once you decide, or once you are convinced that f triple prime is the maximum, our x2 will become 1, and f triple prime of 1 is actually 3 by 8. So what you have to do, you have to take this 3 by 8 and substitute it here. So that will be an upper bound. So if you do that, so the upper bound is 3 by 8 by 3 factorial. So 3 factorial is 3 into 2 into 1. This and this will get cancelled out. You will have 1 by 16 as the upper bound. Okay. So this is the upper bound. So this is how you should compute. So this is computationally heavy, I agree. So you have to do a lot of computations, but it is actually needed. Okay. So there will be 1 or 2 problems where you have to definitely put pen on paper and solve it. Okay. But don't go beyond second order approximations. Okay. So not required. So we'll not ask beyond second order approximations. Okay. Even within linear and second order, first order and second order, there is very minimal chances for second order. Okay. So yeah, so that's all. So these are the topics that I wanted to cover today. So I hope I have covered most of the important concepts. So after this session, maybe tomorrow, day after tomorrow, just spend some time on week 5 and 6. Okay. And solve problems that are related to the concept that we discussed today. Then you will be ready for the exam. Okay. So any doubts you can ask me, or else we can end the session here. And all the very best for your exam. Okay. And we will meet mostly after quiz 2. Okay. Yeah. So I will share this document. Don't worry. And week 7 and 8 is going to happen tomorrow. Okay. And I think we have released the solutions. So I have checked. So all the solutions has been released. We'll also release week 8 today. Okay. And anything pending from our side, mock is also available. Okay. Go attempt mock, and you will get an idea of how the quiz 2 exam is going to be. Okay. All right then. Thanks all. And okay, so 6 and 7 I will upload. I will upload 6 and 7 notes.